I think it's a great opportunity to discuss with all of you my work, my research, and I'm not going to present many results. Rather, I want to discuss with you the motivations which has led me to use second gradient dissipation functionals in fluid mechanics, and some open issues that are puzzling me about the mathematical modeling of mechanical behavior of these fluids. So let's start from the motivations. Why study sedimentation of particles in fluids? It's of course a nice topic, but most importantly it is the first step to understand the mechanical behavior of complex fluids. Let's say fluids with some solid or deformable particles dispersed in them, which are of great engineering interest for many applications. And also the sedimentation problem already presents many of the mathematical and modeling challenges for the study of composite fluid-solid mixtures. And why do I want to use slender filaments? The fact is that when we have biological fluids or engineering fluids, the particles which are dispersed in the fluids are often very small and may display some characteristic shape, slenderness in 1, 2, or even 3 dimensions, like point particles. In particular, I don't want only to treat slender bodies, but I want to treat them as one-dimensional or zero-dimensional objects. And why? Again, because the characteristic size of such particles with respect to the size of the fluid region which is usually under consideration can be between 10 to the minus 6, 10 to the minus 4 times smaller. So the leading order effect of the presence of the particles should be really captured by a point-like approximation. But also one-dimensional approximation are very important because they are the first step in taking into consideration peculiarities due to the shape of these very small particles. And to treat one or zero-dimensional particles, basically what I'm doing is to get rid of boundaries in my domain. And there are 2 reasons which I think are good, but I'm not so sure. We'll see some open issues about that. But the first reason is that the very complicated boundaries which we may find in a fluid with thousands of inclusions, solid inclusions, strongly limit our capability of making numerical studies and to design via numerical experiments new complex fluids. The story of the study of sedimentations, really with having in mind the application I mentioned, so the study of dispersion of particles in fluid started already with Stokes in 1851, and he derived basic and fundamental results. But analytical solutions are available only for very, very simple situations. So perturbation theories and numerical approaches based on perturbation theories has been developed. But still today the real world experiment is basic, unavoidable for the design of new mixtures. Whereas we are able to reproduce some behaviors also with numerics, but we cannot rely on numerics for the design of new mixtures. So since the boundaries have been one of the obstacles in this development, I said, okay, let's try to get rid of them. Another motivation is the fact that coupling different materials to boundary conditions, we all know that may be a very hard task. And in fluid structure interactions, there are, of course, many research is going on, but there are few rigorous mathematical results on fully coupled systems with different materials interacting. And there are possible incompatibilities between the boundary interactions we may want to use, and constitutive theories for the interface may be needed, but again, that's not so easy to have good ones. So I tried to get rid of those boundaries. And it turns out that an essential tool in doing this is a second gradient dissipation functional. Briefly, I recall the Stokes equations for low Reynolds number flow, which are used in studying sedimentation classically. Divergence of the velocity field equals 0 is an incompressible fluid, and then the gradient of the pressure field balances the viscous dissipation. We use the viscosity, and we have the Laplacian of V. Those equations are related to a first gradient dissipation functional. Probably all of you know that the dissipation in this system is given by the viscosity times the integral of the symmetric part of the gradient squared. So I introduce a second gradient dissipation functional, the simplest one that we can imagine. We add the L2 norm of the Laplacian of U, so we have second derivatives. And we also have to introduce a new parameter, L, capital L, which is there for dimensional reasons, but we will discuss its meaning. The new equations we get using this dissipation have an additional B-harmonic term, the B-Laplacian of U. And now I used bold font U and P hat to distinguish between the classical velocity field and pressure and this, let's say, hyperviscous velocity field and pressure. This is an unusual nomenclature. Those equations are not new. Okay, they have been present in literature for in many situations, micropolar fluids, regularization of the Navier-Stokes equations, and many times they have appeared, they have been used, and then somehow disappeared. But why do I need the second gradient dissipation? There is a fast mathematical answer. One or zero dimensional sets have H1 capacity equal to 0. In other words, they are invisible for a fluid if, with my equations and a priori estimate, I can only control the first gradient of the solution. So if I have a first gradient fluid, there is no way of making one-dimensional object interact with the fluid. Okay, the further answer is a little bit more, let's say, complicated, but in a few words, it just says that thinking of a particle, a point particle, which is falling into a fluid, we are obviously led to think of it as acting on the fluid with a concentrated interaction, a volumetric interaction, which is a delta function, basically, concentrated only on one point. And we know that, for many results, that this requires at least a second gradient fluid. Moreover, the hydrodynamic force acting on the slender body has to be defined in some way, and I'm just proposing the easiest way. So we take the slender body, one-dimensional, we take a neighborhood of it, which is now three-dimensional, and we compute the class in the usual way, the stresses, the traction on the surface of this neighborhood, and then we pass to the limit. Two things are important. First of all, this limit is well defined. Now I won't go through the details because we are a little bit late. But the second very important thing is that if the divergence of T, which is the stress tensor, is regular in the sense that it is an L1 function of all of the space, then the force on this one-dimensional object vanishes. So we see that we really need a higher order medium to be able to model the interaction between 3D fluids and 1D objects. Now, in the last few years, I obtained with, of course, my collaborators, some results, mathematical results. I briefly recall them. We obtained well-posedness of the differential problem related with general bounded flow, where a one-dimensional object goes around with a prescribed motion and drags the fluid. Then we attacked the coupled problem of the free fall, in the sense that the object is falling, it drags the fluid, but the fluid is interacting with the viscous force we just discussed. The steady free fall is a little bit easier. Also, in the linearized low Reynolds number regime, analysis of geometrical features can be done in a very precise way. The unsteady free fall can also be treated with classical techniques, provided that we put everything into a big box, because working with all of the space have some technical problems, but they are not really relevant here. It is important to say that, as it was known, the regularizing Laplacian terms provides with a global in time existence and the uniqueness of strong solutions for the coupled problem, which is a result which is still lacking for standard fluids. But now we turn to the open issues, which I would like to discuss with you. First, the meaning of the parameter L. I have a hint, but which is not a proof. I computed the drag force exerted on a point particle uniformly translating in a fluid with velocity, let's say, minus u, with second gradient dissipation. And that drag force is 6 pi mu L, which is the new parameter, times the velocity u. But you see that that quantity is exactly the drag force exerted on a sphere of radius L in a classical fluid. That is the 1851 result by Stokes, Stokes formula. So this suggested the interpretation of L, this parameter, as an effective thickness of the one-dimensional or zero-dimensional object in this case. I think it's a nice interpretation, but I have to admit that it is not easy to generalize this interpretation to the case of filaments or to the case of dispersion of many particles with probably a random distribution of their characteristic size. So this is still an open problem of interpretation. Another open issue is the velocity field U. Dimensional analysis says that it is a velocity field, but it is not the real velocity field. It is similar to it, but definitely different. And I tried to obtain that U with, let's say, average procedures, but I wasn't able to do that up to now. We may think that since to study the properties of suspensions it is enough to know the hydrodynamic interaction between particles, which is mediated by the fluid. So we can hope that this new field U doesn't give the velocity field, but allows us to obtain the correct hydrodynamic interactions. Another open issue, which is a big one for me because I'm not a numerical analyst. And I'm looking for some numerical analysts to help me at this point, because we need numerical simulation. It is easy to devise methods for steady flows, but they are of little use, because when we have more than one particle, basically steady solutions are not available. Moreover, I wanted to get rid of boundaries because I thought that it would have been a major advantage in numerical simulation, but I have to do numerical simulation to prove that this is the case, and actually also to compare the results of this modified theory with the classical and the standard results of the slender body theory. And the last one, but important, since some months we are working on the free fall of the formable one-dimensional objects, and of course the first point is to define the viscous interaction, now not in a global way, because but we need a density, a linear density of forces acting on the body in order to understand how the fluid can deform, can act on the shape of the body. And up to now I only have this first proposal, let's say, which is which may be a little involved, but the idea is simple. I take the neighborhood of the one-dimensional object, I make a lot of thin slices of this neighborhood, and then I send to zero the thickness of the neighborhood and the thickness of the slices. Okay, this is one idea, but I'm still not sure that it is completely okay, and of course you can see that there is some arbitrariness in this choice, which I would like to remove. Summarizing, if we want to use one-dimensional filaments, then we need second gradient dissipation. This also allows for nice mathematical results, which sometimes are not easily reachable in the classical setting. But many open issues have been risen during this research, and since it is based on a mathematical approximation for the purpose of a mathematical treatment of real-life situation, the interpretation, the physical reinterpretation of new parameters and of the whole construction is sometimes difficult and still unclear even for me. Thank you. Question number one.
Can you explain a little bit better how you are calculating this force on this point?
Yeah, it's, well, we don't need a slide. In order to calculate the force on the point, I used two techniques. First, I computed the force on a sphere, and then I send the radius of the sphere to 0. If you do this in the classical setting, you lose everything because the solution is divergent. But in this setting, the fundamental solution of the Stokes operator is continuous in the origin, so you get the coefficient of the fundamental solution is the drag force.
Are you the work of Hans Weinberger on the dropping of bodies in viscous?
Yeah, sure. Yeah.
This way or
Yeah, there are that work with some subsequent treatment by Galdi, you may know, has inspired our treatment of the. Yeah, I didn't reference anything because the literature is huge, but yes, we started from that.
I don't know if regarding your new vector field.
Yeah.
You probably know the work of Howard Brenner. That advocated for many years, not always successfully, additional vector field and velocity fields. If you know
Brenner or Brennan? Brenner. Happen Brenner. So, yeah.
He does work on slow viscous flow.
Yeah, he also has a monograph, important monograph on the free fall particles, but I didn't know that. Yeah, I will look for that.
Okay. Question here.
There is a state of Matrix crystals, one director. Maybe it's also interesting to consider your hydrodynamics with slender particles as the directors. Isn't it
yeah, maybe. Actually, so I don't know. You're saying that this procedure may be useful in that case, or okay? Yeah, I don't know. Yeah. Okay. Actually, we are trying to apply gamma convergence, but you see here the dimensional reduction is not on the body, but on the complement of the domain. So the domain remains 3D, and the first, we weren't able to find the limit, neither the lim sup now, because in one case with the simple choices you get minus infinity everywhere or blow-ups. It may be, but the faraway boundary doesn't change too much. It's really the fact that the sphere goes to one point, but the surrounding is always three-dimensional. So, but we're working on it.
Thank you very much.